We're very happy to have here today Thomas Lam from the University of Michigan, and he's going to give an introductory lecture on positive geometries. Thank you very much.
Thank you for the introduction, and thank you, Matteo. Thank you, Lauren, for inviting me to speak. I'd like to advertise to the speakers in the next few days that this blackboard has the best array of colored chalk I've seen. I counted it. It's more than 10 colors, and it's also fancy chalk as well. So I want to talk about positive geometry, and so let me start with a cartoon. This might be something you think about when you think about complex geometry. It's the Riemann surface. Here's a real plane curve. Now, this is something that you might think about if you're thinking about real geometry. Here's a visual picture of a positive geometry. This blob here, this is the kind of thing. So this is actually with the correct equation, this is actually a positive geometry. So that's just to put us in the right frame of mind. And in positive geometry, we think about properties of these kinds of blobs. Okay, so I want to repeat something that Yara talked about. Positive geometries came up in physics from studying amplitudes, and I want to sort of repeat the philosophy that Yara had mentioned. So in amplitudes, we're trying to understand these things called these functions called amplitudes, and there's a perturbative expansion, and the first term in this expansion is a rational function. So I'll only talk about rational functions, mostly just rational functions today. If we're working perturbatively, we want to determine a rational function. On some space, we want to find a rational function. And Yara mentioned that there's a program to determine this amplitude by putting some constraints on it. If you put sufficiently many constraints, maybe there is only one left. And the kind of constraints that one looks at are the poles and residues of this rational function. And sort of the philosophy of using positive geometry to study amplitudes is we're going to study things like this. So these geometries. And we're going to associate with the geometry something that's akin to poles and residues, which is the combinatorics of the phase structure. So in physics, common to say boundaries. So there'll be facets, codimension 1 faces, and then there'll be codimension 2 faces, and so on, and then all the way down to vertices and edges and such things. And the philosophy is that your rational function is constrained by some kind of information about where the poles are, what the residues are. These poles and residues are supposed to match the combinatorics of faces and boundaries of some geometries. So let me give the definition. So that's the philosophy. So definition. So we're going to look at a pair x greater than or equal to 0. So d-dimensional positive geometry. The x will be a complex projective algebraic variety. Also d-dimensional. And we'll assume it's defined over the reals and it has some real points. This thing will be a semi-algebraic subset. And what this means is it's a subset that's cut out by polynomial equations and polynomial inequalities, and you're allowed to take unions and intersections and so on. So we have some. So what is a algebraic variety? Is something that's defined by a bunch of polynomial equations. Projective basically means it's compact. And inside it, I'm going to look at real solutions to those equations that, in addition, satisfy some inequalities. Okay, so when is such a pair? So this thing is sitting inside here. So this, so x greater than or equal to 0 is sitting inside. So the real point, so real solutions to the same equations, which is inside x, inside complex points. So when is this thing a positive geometry? So it's a recursive definition. So if D is equal to 0, so it's 0 dimensional, then we can just ask for it to be a point. And a point is a positive geometry. And in this case, we also define a function here. The function is plus or minus 1, and it depends on basically an orientation of the point. And if D is bigger than 0, then the condition is every facet of x greater than or equal to 0 is a D minus 1 dimensional positive geometry. And there exists a unique D form. It's called omega x greater than 0. Usually I just shorten it and it's fine. Omega x greater than 0. There exists a unique top form on this variety x, satisfying a bunch of conditions. So the simple pose, let's write it more carefully, with pose only along the facets F. So these poses are simple. And there's some residue condition. So when you take the residue along the facet, along the Zariski closure of the facet, so just some technical point. If you take the residue along the facet, then you will get the canonical form of the facet. So this omega is called canonical form. So I'll give some examples of how this works. So this thing is a D form, and this thing is a D minus 1. And if you go all the way down, if you keep taking residues, so if you keep taking residues as you take facets of facets of facets, you eventually get down to points, and then the residue should be plus or minus 1. There are some technical things that I'm sweeping under the rug. For example, what kind of singularities you allow. Also, there's an issue of orientation and so on. I'll sort of not go into the details of that right now. Let me just start off with right away with an example. So yes.
When you go to a facet, you like a D minus 1 dimensional positive geometry to find like one set, you take the facet of x more than or equal to 0, but don't you need like two sets to define like a variety and then a semialgebraic set within it?
Yes. So right. So the when I say facet, there's basically the facet, which is the positive part, and it's the Zariski closure. So it's a pair. I'm being sloppy with the notation, which is if the ambient space is understood, then I'll just write the semialgebraic set in the notation. Thank you. Yes.
Can you avoid writing at the bottom of the board if possible? It's a bit hard to see this people's.
Oh, okay. Yeah, the board actually goes pretty high, but I'm not actually tall enough. Like there's a lot of space up there, so I will try to stretch. So yeah. So so zero-dimensional positive geometries are points. Well, one-dimensional ones. So what about d equals 1? Let's take our x to be P1. So P1 contains the real projective space, which is just a circle, which contains the real line. So real projective space you can think of as the real line plus 1 point at infinity. And one possible choice of a positive geometry is an interval. So you can take x greater than or equal to 0 to be the interval. And in this case, it does satisfy this recursive definition, and the form is this one. Already in this case, it's actually interesting to think about this one a little bit. So first of all, what is this? This is you're supposed to solve a system of equations to calculate the canonical form. What are you supposed to look for? So you're supposed to look for a one form. A one form is a one form in local coordinates will look like a rational function times dx. So you're searching for omega is equal to something like q of x over q of x dx. It should have the property that it's only got poles along the facets. What are the facets of the interval? It's the two endpoints. So x is equal to a and x is equal to b are the two endpoints. So whatever you're looking for, it's got exactly two poles, and these two poles are simple. It's at one of the poles is at a and one of the poles is at b. And the other condition is that when you take the residue at the poles, you should get, well, plus or minus 1. Now the plus or minus, which sign you get here is determined by an orientation. But in this case, you can see that there's actually a compatibility. You have to take one of them to have plus 1 residue and one of them to have minus 1 residue. Now, let me come over here to see if I can explain that. So you might think, here's my real line, here's my interval a to b. These are the two facets of my interval a, b, so the boundaries of my interval. I want to put, I'm looking for one form that has poles exactly here and here, and it's supposed to have residue 1 at here or minus 1. 1 or minus 1 in the two places. We determine it by giving orientation, so maybe it's 1 here and minus 1 there. But for example, if you ask that the residues are both 1, then there's no solution. There's no solution to this problem. So if you did something like omega is dx over x minus a plus dx over x minus b. So if you did this instead of that, then you find that this has a pole at infinity. So this is the importance of thinking about an ambient space, which is a projective variety. So this looks like it has residues which are 1 or minus 1, but it's not the canonical form of a positive geometry. It's there's another pole at infinity that's causing a problem. Yes.
Just about maybe the diagram you actually just erased with the elliptic curve. So one was a nodal one that you identified this bounded region as a positive geometry, but the other one also has a sort of bounded region.
Okay. Yes. So I was supposed to make this talk kind of really introductory, so I didn't want to and possible for physicists. So I'm going to say something that might not be understood by physicists. So if I have an elliptic curve, then it has a holomorphic one form. And therefore, it cannot be the x of a positive geometry because there exists unique here. So you can modify a solution to this problem by the holomorphic one form of the elliptic curve and get another solution. So there might be another version of this thing for genus 1 curves. So on the smooth genus 1 curve, you can't build a positive geometry on it. because of this unique condition. Yeah.
You're back.
Yeah, so but when it's the nodal curve, then you can you can discuss about how to deal with the singularities, and it is a positive geometry when you're careful enough. Okay. Okay, so let me do another example. So this is typical example of something that's two-dimensional example. So this is a region. This is quadrilateral. So we're thinking of this quadrilateral in R2, which is sitting inside P2. And this is also a positive geometry. It has this guy has canonical form. Omega is equal to 4. This particular formula. So it's a true form. And if you check the degree of this, you see that it doesn't have a pole at infinity. You can clearly see that it's got 4 simple poles. These 4 factors of the denominator are exactly the linear equations that cut out the 4 facets of this of the quadrilateral. The numerator is a little bit mysterious though. So I claim there's actually essentially no choice in this numerator. It's defined. There are 2 possibilities, either this or negative of it. I will get you one that works. So what is something that I haven't said that much about is what is this operation residue? So let me not define it carefully, but just give an example. So residue is so the residues that I took over here are the Cauchy residues, so familiar from complex analysis. What about this guy? How do I take a residue of this? I can try to take the residue of this thing at y is equal to 0, which would correspond to this this facet here. This chalk. So let's try to take residue of y at y equals 0 of this omega. So you can also do it with a Cauchy integral, but I'll just do it algebraically. What we do is we extract dy over y. So there's going to be a sign. I'm going to write it as dy over y. Wedge some other thing. In this case, it will be 4 minus y. Y 4 y dx. So I wrote it as dy over y wedge a1 form, and then the operation that we do is to take the residue y equals 0. We just remove the dy over y, and then we evaluate this one form by pulling it back to this line. So we get rid of this, and then we take the remaining one forms. 1, 2, 5, dx, and then I'm going to evaluate at y equals 0. When I evaluate it at y equals 0, x, y is equal to 1 x, and then here's 4 minus 2x dx. Yeah, sorry, I'm going so low. The 1 plus x's cancel out, and you recognize this. If you write the partial fractions expansion of this rational function, you recognize that it looks like this. So it's exactly the one form on this line, which has a simple pole here and a simple pole here. Okay, and 4 plus 4x minus y is chosen, so it works if you do this for any of the lines. And you can see from this that actually it's kind of a little bit unclear that there is a solution to this problem. You're asking to fix you're asking for a true form with 4 linear things in the denominator, something in the top, and it's going to be, the thing in the top has to be linear for there to be no pole at infinity. And then you're fixing the residues along all four of these lines. That's somehow seemingly too many conditions to have a solution. But there is, and the solution is unique.
How sensitive is this? Like if I change that fourth point of the quadrilateral, would it still exist?
So the next the theorem is that every convex polytope is a positive geometry. So it does work if you move the vertices.
Right, question. If you have cusp curves like back in 1D, we have a cusp curve. Are there examples when you have this 0G basis with these cusps?
What region are you looking at?
I'm just saying, can I have cusps, the curves?
I think that's so singular curves have been studied. So there are examples of positive geometries where one of the boundaries involves curves with cusps. Yeah. But I don't know exactly the range of examples involving curves with cusps. I would draw some pictures of ones in a while. So maybe this was example 1. This was example 2. Now example 3 is that any convex polytope inside R to the D, this must be top dimensional. And then you put an exit. Here's an example. I'll discuss in a moment how you might go about proving this. But you can also draw other more exotic things. So here's a half disk. It is a positive geometry. This we write down. It doesn't have to always be convex. Something looking like this. Turns out to also be a positive geometry. And the example that I had right in the beginning, this guy has canonical form dx dy x cubed. So the equation of the curve is y squared equals x cubed plus squared. Yes.
Is there a generalization to
Generalization to what? I will. Okay, yeah. You're moving a bit ahead. I will start talking about flex right in a while. So yeah, I will come to more examples. So I'm just gonna. So the next one is conjecturally. So this is. Just put a star here. Yes, Yara's talk. And there's a whole. This is not just one family of examples. There's a loop amplituhedra, and there's just a huge zoo of things. Many from physics, which we are conjectured to be positive geometries. One big class, if you know what they are, is you can take projective toric variety. So this is a projective variety, normal variety containing a algebraic torus, dense algebraic torus. And the algebraic torus comes with a natural form. And the form will have poles exactly along the torus orbit closures, the torus invariant divisors. So if you know what toric varieties are, that's an easy example. Another class of examples. So yeah, I mean, this is not quite the whole thing. I also should tell you a semi-algebraic set. So there's something that's called the positive part of the toric variety, and its closure is the semi-algebraic set you take. I won't say more about this. Another example is the example that was mentioned in Yara's talk, which is the talking nonnegative Grassmannian. And that belongs to a bigger class examples called talking nonnegative flank varieties. These are also examples of positive geometries, and these things are sitting inside thing of P or. So there was a question about taxonomy flag varieties. I don't know. I believe that they're so currently the definition of positive geometries requires them to be finite dimensional. But certainly there are strata within taxonomy flag varieties which I expect to be positive geometry. To tie to Christina's talk, I think I should mention that there's a general kind of broad sort of conjecture that cluster varieties should give rise to positive geometries in the following way. So if you have a cluster algebra A, we can look at the corresponding cluster variety. Let's call it X. Now this thing is not projective, so this is going to be an affine variety. So the cluster algebra gives you a lot of variables and a lot of equations. And I'm just asking for the solutions to all of those equations. In other words, I'm looking for some space whose ring of functions is my cluster algebra. On this space, actually, there's a very nice positive part, which is x greater than 0, which is just all the points where all the P, where xi of P is greater than 0 for all cluster variables. It turns out that this is so you can define this set subspace of your cluster variety with respect to one cluster or with respect to all clusters, and because of the fact that the exchange relations are positive, this is a well-behaved subset of your cluster variety. There's also a natural top form, which is there's an omega, which is you can take dx1 over x1 wedge dxt over xd, where x1 of 6d is a C, is a cluster. So you choose any of your clusters and you build this V-log form, and an easy check with the exchange relations is that this top form is invariant up to sign when you perform mutation. So this is just a local calculation. You look at the formula xx prime is equal to something plus something, and then you calculate what happens to the d-logs. So here's a setting where there's a natural candidate of some positive part and a natural candidate of a canonical form. But you can't quite yet talk about a positive geometry because this thing is not projective, and it doesn't. You're not allowed. There aren't any facets yet because you when you look at the facets, you kind of leave the space. So a vague conjecture, is that X can be compactified so that closure is. And the basic example where this seems to have been studied pretty well is the case of these the Grassmannian. So Grassmannian, so there are some sort of technical definitions involved in which involves what you're supposed to do with the frozen variables in here. But one case here is to take the Grassmannian and take the total non-negative Grassmannian, and you find what happens is that all the facets are also cluster varieties, and then facets of facets are as well, and then everything is also a positive geometry. So I don't know how much we know about how to compactify cluster varieties. And then there are another example that's kind of important is, for those who know what this thing is you can take moduli space of stable rational curves, marked curves, and that's also gives an example of a positive geometry. So in this case, you take this projective variety, and what you do to get the positive geometry is you take the moduli space of n points on P1, and then you look at the real points of it, and you pick one of the connected components, and you take the closure. So this is closure of connected component. So there's a big range of things that are examples. Yes.
Is there anything about the fixed process? It's not negative part from the since they come from public anything.
Not that I know of. So the examples, yeah, the examples that we have do have nice. A lot of them have phase posets that are polytopal. Like for example, this one has the same phase poset as the sociohedron, which is a polytope. You certainly have phase posets that aren't polytopal, but they're also still very nice. I don't know what kind of phase posets you can get. Yes.
And so very high dimension when we take the residues all the way down. And is it always, we always know that we can further take residue in the sense that what if we have square root set? Because I mean, we're looking at a very high polynomial and I'm taking residues and then plug in the solutions. Then once you hit like these square root factors, and then we did understood how or like how to do next, or we can determine whether it's a positive.
So one case where you might seemingly encounter a square root is if you took this guy and wrote down the form, which is something like y over y, whatever the equation of that is, which is y squared minus 1, say. You don't have to explicitly solve the square root. You can take residues by doing the thing that I said, which is take the equation that you're trying to take the residue with respect to, a local equation, and then extract df over f. So if but you can do it locally at one of the solutions. So you don't actually have to solve your square root to do it. So this case, if you take the residues of this, you might think you need to write square roots, but you don't actually. There's a way to do it just purely rationally. We can talk more about this later. Yeah, this example might look like it has square roots, but it is a positive geometry and everything is rational.
There's another question.
Yes.
Let's say assume you make conjecture and the cross algebra the product variety should be a positive geometry, and then the differential form should be unique. How do I think of this uniqueness? What does uniqueness mean?
So in the case of in the case of this in this case, so this is a cluster algebra. In this case, one way to think of it is that the divisors where the form. So you look at this thing. This is a top degree form, rational form on the Grassmannian, and it has simple poles along things called positroid divisors, and in some sense and in fact it has this guy has no this guy is a special case. This guy is a special case. The canonical form has no zeros. So in fact, the form is uniquely determined up to scalar by where the poles are. So if you know where the poles are and it has no zeros, then you already know it up to scalar, and that's the kind of uniqueness. So you fix the scalar by asking for all the residues to be 1 when you go all the way down. Okay, so let me say, so I gave a lot of examples. I mean, some of them will not be familiar. I mean, some of you won't be familiar with all of them, but that's okay. So I just want to give you a feel that there's a lot of these things around. What kind of questions do we think about in the subject? one of the one of the things is to continue this and find more examples and prove more examples of positive geometries. Another question. So one question is look for more examples, and another question which is to find more relations to physics. And the relations to physics, they don't all fit exactly the paradigm of how it worked for the amplituhedron that Yara explained. Sometimes positive geometries are related to physics in slightly different ways to how the amplituhedron is related to the super Yang-Mills amplitude. So they appear to have other to come up in physics in many places, not just in super Yang-Mills. And another broad thing that one thinks about in positive geometry is to find formulae for this guy. So if you have a positive geometry, then you want, and especially if you're interested in amplitudes, then one of the things that you want to calculate is the canonical form. And every formula that you have that gives you, so if you imagine you have many different ways to calculate this canonical form, then you have many ways to figure out what this amplitude is, which is kind of the answer that you're looking for. About the first thing, let me comment because there are a few questions about this. Basically, there are, I think of right now, they're basically sort of three general classes of examples. The examples that come from physics, and most of them, unfortunately, we're kind of behind in math. Most of them are still conjectural, the examples that come up in physics. There's a class of examples that come up in representation theory, or basically in geometry of algebraic groups. So those are the examples which are like totally positive blah or totally negative blah. A specific example is the theorem is that token of negative flag variety is a positive geometry. An example of a conjecture is the token of negative part of this group compactification is a positive geometry. And then there's a third class of examples that sort of are more algebral geometric. For example, the ones that come up with a nodal curve. The pictures that I drew. So they're kind of sort of three classes of examples. I don't know if it doesn't seem like we're anywhere close to start classifying these things, but they do come up in lots of places and different perspectives to look at them. Okay. Let me talk a little bit. Let me talk a little bit about formulae. So I want to sort of repeat what Yara said. So Yara talked about one particular way to approach finding a formula for the canonical form, which is to triangulate. So let's just theorems. So I'll just form. So this holds for positive geometries, but I'll just formulate in terms of polytopes. So if you have a subdivision of a polytope, then we have a formula for the canonical form. This is actually very easy to see. Let me just give an example with already we had an AB. So this is my interval. I can subdivide this interval by putting a point C here, and now I have two other. So now I have three positive geometries. I can take the canonical form of the interval AB, and I can compare it with the canonical form of the interval AC and CB. Sorry. And if you remember my formula for the canonical form of the interval, you see that the simple poet C cancels out when I write this, and then you get this formula. And that's and essentially the same proof works for polytopes. Just the same proof that your simple pose that if you take your polytope, here's my polytope, I cut it into two pieces. This is my Q1, this is my Q2. Then Q1, the canonical form of Q1 will have a pole along here, but Q2 will also have a pole along here, and the poles will cancel out. The residues will cancel out. Yeah, so the residue along here will cancel out. However, if you take the residue along this facet, then you find that you get a subdivision of this interval by this interval and this interval, which by induction you already know works. So the proof of this is straightforward. It's just a feature of how subdivisions behave with taking precedence of a polytope. Let me give one more. So this is the approach that has worked so far and has led to a lot of activity for the amplituhedron. And in fact, it's basically I think this is the only way we have to find the canonical form of the amplituhedron is via triangulations right now. However, for other positive geometries, there are actually sometimes many formulae for the canonical forms. Let me just give you one, which is so P is a polytope. Then there's an explicit formula for the canonical form. So what is this notation here? So I'll do it by example. So this is volume, and this is the dual polytope or polar polytope. So what I'll do is I'll take my P to be the interval AB. So D is equal to 1. And then I will look at the polytope P minus X, which is a translation of this. That's A minus X minus X. And then I'm going to take the dual of this, polar of this. So if you assume that 0 is between minus X is less than 0, is less than B minus X. If you make these assumptions, then the dual polytope or polar polytope is also an interval, and it's the interval given by 1 over A minus X, 1 over B. So that's the definition of the dual polytope. And now, if you want to calculate the volume of this thing, what's the volume of this? It's the length of the positive part, which is 1 over B minus X, plus the length of the negative part, which is 1 over X minus A. So the formula that you get here is this thing times dx, which is exactly the formula that we had before. Okay, so it's still an open problem to find a formula like this for the amplituhedron. And I think this is one of the most enticing problems in the subject, especially at the place interacting between math and physics. Is what if P isn't sitting inside Euclidean space or projective space? It's sitting instead inside a Grassmannian. How do I take the dual? How do I take the polar? What is the dual of the amplituhedron? And that I think is still, it's one of the most exciting problems. So let me say something about sort of one of the general things that we do with positive. So I want to talk about some applications. We already know that one of the applications of positive geometry is you give me a geometry, by definition, it uniquely determines a canonical form, which in the case of the amplituhedron should produce for you the scattering amplitude, which is the answer to questions in quantum field theory. But from a mathematical perspective, one natural thing that you might do, so if you have a positive geometry, a kind of natural thing to do is to try to write down the following integral. Because you're given a top form on a space, and you're also given a cycle, a chain. You're given this subspace with positive geometry, and you're given a form. It's kind of natural to try to pair them and integrate. And unfortunately, the way the axioms are defined, this never converges because it will. This thing always has a pole along the boundaries here. This has logarithmic divergences in every direction. So this never converges. But what's interesting is that there are many applications where you put something here. Maybe you might call it a regulator. You insert some prefactor into here to make it converge. And in different situations, you insert something different, and you get different functions of interest. So the situation of the amplituhedron is a little bit cheating. In the situation of the amplituhedron, you put in here something called a delta function. And what the delta function does is it makes it so that there's actually no integral to do, and you just it's just a residual problem. It's purely algebraic, and there's no transcendental part. But there are other examples, and maybe one of the ones that one of the main ones for the purposes of talking about amplitudes is the string amplitude. Is let's say open tree level. Those are some adjectives here. The string amplitude is obtained by taking this to be M0 end. So, and then you put something here y to the s. There's a particular function that you put here. It's called the Cohen-Nielsen vector. And this becomes a function, analytic function in terms of S. So this is a basic example of how one might use positive geometries and the canonical forms to build other things. So in this case, you integrate over your positive geometry of the canonical form, and then you put in something that makes the integral converge. So what kind of functions do you get? So for n equals 4, you get Euler's beta function out of this construction. Okay. Yeah. And there seem to be many places where one can find integrals that are interesting. For example, integrals that come up in sort of study of hypergeometric functions, which you can set up in a way that looks a little bit like this. I think in the how much time do I have? Okay, so in my remaining time, let me try to mention one recent result and application of positive geometry and canonical forms. The setting is I'm given a hyperplane arrangement. So I'm given a bunch of projective hyperplanes in projective space, and I'm interested in the complement. X is obtained to projective space by removing all the hyperplanes. So what does it look like? So this is actually what it looks like for this case when n is equal to. This is actually a picture of n05. Though I'm drawing an affine picture here. So what I'm looking is I'm taking the plane, but sort of over the complexes, and I'm removing all the lines that I've drawn. That leaves a lot of regions here, and these regions are all positive geometries because they're all polytopes. So So this is one positive geometry, this is another one. So in this picture, and this seems to be something that is coming out more and more often, is that you take some projective variety, you remove a bunch of divisors, and there's a lot of connected components left, and sometimes these are all positive geometries. I don't know how general this statement is, but in this case it's easy. Let's suppose there are enough hyperplanes so that every region that's left over is bounded, and so now every region that's left over is a polytope, and all of them are positive geometries, and all of them have canonical forms. And so let me formulate a theorem which is sort of an application of canonical forms to hyperplane arrangement complements. So let's pick a flag of subspaces, and I'll assume that it's in generic position with respect to the edges, and then a region R of this X, let's say over the reals, is called K bounded if it doesn't intersect the K piece in the flag. So this flag means that this is 0-dimensional, 1-dimensional, d minus 1-dimensional, d-dimensional. So dimensional K with empty set, but oops, sorry, it intersects the K one and does not intersect the K minus the first one. And the theorem is that this is upcoming work with CRISPR, is that for each K, the set of canonical forms of regions that are K bounded gives a basis of the K cohomology of the complement. So let me say what it is for top forms first. So when K is equal to D, I'm looking at regions that don't intersect this hyperplane. And each such region has its own canonical form, which is the top form. I take all of these top forms and I think of them as cohomology classes, and they will form a basis of cohomology. So this is closely related to work of Green and Saslavsky from the 80s, more recent work of Yoshinaga. But this, we formulated it in terms of positive geometries here, and it's and we hope something like this is true not just for hyperplane arrangements, which is the sort of easiest case of something like this. Let me do an example, but just before that, let me just say, let me go straight to an example. So in this in this particular case, I want to draw things projectively. So I'll draw so these two lines are parallel, so they meet at the same point at infinity. So I'm going to draw my I'm going to redraw this arrangement like this. And the big circle is the line at infinity in P2. And now I have to pick an F. So I just have to pick an F that doesn't intersect anything in a funny way. So this could be my F1, and I'll put, this is my F0. So that's my F1. So F1 is this line, F0 is this point. What the theorem says, I'll take K is equal to 2. So I take K equals to 2. I'm looking for regions that don't intersect the pink line. And let me, when the colors, so here's one region. See if I run out of colors. And maybe this is not so, maybe this is not so fun. 1, 2, 3, 4, 5. Let me just check. Yes, okay. So there are 6 regions that don't intersect the pink line. The dimension of H2 of this space is equal to 6. Actually, this X is M05. And the basis for this space consists of these particular 2 forms. The 2 forms are the canonical forms of these 6 regions. Thank you.